Okay. Now I'm recording. Now they can hear me. Okay. All right. So now what we're doing here is probability for, we're looking at probability again, okay? Now that's what we're looking at. Okay. Now, this is something we did this is actually, I think, one of the things we left off with last time. I did email you the notes, so the notes are in your inbox. So remember, for two events to be independent, what that means is the probability that one of them occurs is not affected whether or not the other event occurs. So I think what we actually said was events A and B are independent if the probability that event B occurs is the same regardless whether event A occurs or doesn't occur. It's the same regardless whether event A occurs or doesn't occur. And what's nice about seeing events, what's nice about independent events is if you want to calculate the probability that both events occur, you just have to multiply like this. That's all. So if you want the probability that events A and B both events occur, if they're independent, you just multiply like so. No, that's all you have to do. And we saw some examples of this. For instance, I think one of the examples we saw was flipping a coin and then rolling a six-sided die. I mean, really, if you think about it, in that example, yeah, we flipped the coin, and whether the coin landed heads or tails, that did not affect, whether we rolled the die or not. We rolled the six-sided die no matter what. So I did try to show you why they're independent, but if you think about it, yeah, they should be independent. It's not like if we flip the coin and the coin lands on heads, then, we have to roll the die this way. And if it lands on tails, we have to roll the die another way. So, I mean, hopefully that makes sense. I'm just trying to illustrate that if you just think about it, yeah, the event should be independent. So here's another quick example. Here, we're looking at tossing a coin into the air, but we're doing that twice. We want the probability that the coin lands heads up both times. Well, hopefully you can see, even before I show you the next slide, that this event, these two events are independent. The events that the coin lands heads up the first time, and the event that the second time we toss it, the coin lands up heads. So in other words, here, let me say it this way. What's happening is we're tossing a coin, into the air. We're seeing if it lands heads or tails up, record that. Then we take the coin and throw it and toss it into the air again. If you think about it, well, yeah, those two are independent. What you get, if you get heads or tails on the first toss, that shouldn't affect whether you get heads or tails in the second toss. Why would it affect it? It's not like with a deck of cards where if you take a card out, you know what the card is, jack or king, whatever, and you don't put it back. Well, the next card you draw out will be affected. This is one card less. It's not like that it's not like that here. Okay, so both times we expect the probability to be a half. In other words, since they're independent, all we have to do is get the probability we get heads on each toss, since they're independent. I didn't write out what A and B are, but you could say let A be the event that the coin lands heads up the first time, and B be the event the coin lands heads up the second time. We want the probability that A and B occur in this case, that on the first toss the coin lands heads up, and on the second toss as well. So we're really using this equation here. In this case, A is the event. On the first toss, the coin lands heads up. B is the event the coin lands heads up. We want the probability of A and B. So what this is saying is we just need the probability of each and multiply. What's even nicer about this example is both probabilities are the same. So it's a two-sided coin, the same coin actually. So what we end up getting is a half for each. Both sides are equally likely. So the probability that both we get heads up both times is a fourth. That's what I'm trying to say here. Again, the notes are sent out to you, so if you haven't seen them yet, they're in your inbox. And really, just to bring this home, so to say, I'm also showing you by considering the sample space. I mean, here we're tossing a coin twice into the air. So listing out all the possible outcomes, it's really not terrible to do. There's only 4 possible outcomes. Why? We'll actually see when we get to what's called the counting principle. Well, actually, we just listed them all, I guess. But here you can see these are all the outcomes we can get. We want this only. Well, there's 4 equally likely outcomes, right? The event we're interested in, the outcome, excuse me, we're interested in, as I'm saying here, is just this one of them. So the probability is 1 out of 4. Well, that's what we got already. So yeah, that should make sense. Okay, that works. Good. Okay, so that's one easy example. All right. Now, you might be wondering though, wait a minute, what if the events in question are not independent? If you go back to that, well, I said the card example, but another one we'll see shortly is that marble example we'll see again. Where you have a bag of marbles, you're taking a marble out, but you don't put it back, and then you take a second marble. Both events that the marble is chosen is red. The first one is red and the second one is red. We saw that last time. Those 2 events are not independent. Can we get the probability of both marbles in that case being red? Well, we're going to need this idea, conditional probability. So what I'm trying to say is this is something new we're going to work with, conditional probability. I mean, here it's really just notation so far. If you have 2 events A and B, the probability that event B occurs, given that event A has occurred, is written this way. I mean, essentially what's happening here is we have B, the vertical bar is written as given. Or if you want, you can think of it as such that. So this is the probability that B such that event A occurred. What they call conditional probability, because we're looking at the condition that event A has occurred. And these are just some important, notes that I brought up. Although actually they shouldn't be there because they're on the next slide. Okay, I forgot to delete those, that is. Here, let me do that quickly, actually. Okay. There we go. I forgot to delete those because I put them on the next slide to be a little more, organized. Basically, it's not commutative. That's the first thing I wanted to point out. In other words, if you have 2 events, A and B, these 2 may not equal each other. I mean, one of them may not even make sense. Oh, we know. But they don't have to equal each other. I don't want to say they're never equal to each other, but they're definitely not always equal to each other. So you can't assume that the probability of B given A equals the probability of A given B. You cannot assume that they're equal. And also, really, if you went back to the definition of A and B being 2 independent events, that's really the same thing as saying this. That's really the same thing as saying this, that if A and B are independent, then this has to be true. This has to be true. Okay. Good. Okay. So that's what has to happen here. Basically, it's just from unfolding the definitions, right? I mean, I did say it already. It's in the notes from last time, if you remember. I know I didn't post yet, but you still should remember, though, that for A and B to be independent, the probability that B occurs is the same whether A occurs or does not occur. Well, if A does not occur, remember what this notation is. This is the complement of A. The complement of an event occurs when the original event does not. So in other words, the complement of A will occur when A does not occur. So in words, we actually have these equalities. And here the top one holds if you interchange the roles of A and B, so to say. You know, the probability of A occurring does not depend on whether B occurs or does not occur, whether B occurs or its complement occurs, in other words. Which really means that the probability of A, given that B has occurred, is the same as the probability of A. So it's really just trying to say symbolically the definition of two events A and B being independent. Now here I said if A and B are independent, then these equalities hold. The other way around I want to say is also true, that if you have these equalities, then they have to be independent. But I want to check into that first. I want to be very careful. But definitely, if A and B are independent, these equalities are true. All right, let me just pause the recording because I don't want to, what do you call it? I don't want to go too far over. Okay.